All right, here we are in section 9.4 on the derivative. Here we'll look at rates of change, slope of the tangent line, the derivative, and non-existence of the derivative. So the derivative can be used to solve both problems to the right. In each case, this is a rate of change. So we can kind of find the equation of the tangent line, and we can also find the instantaneous velocity of a falling object. So these are the two problems they're talking about. And the average rate of change is going to be what we're using here. So for y equals f of x, the average rate of change from x equals a to x equals a plus h, some small distance, is f of a plus h minus f of a over a plus h minus a, which all comes down to this f of a plus h minus f of a over h. And the key thing is h cannot equal 0 because then we divide by 0, so that doesn't work. Note the numerator and the denominator in 1 are differences, so 1 is actually called a difference quotient. So this is a difference quotient here, and we've used it before in different things, and so this is difference quotient. Now the average rate of change of a distance with respect to time is also known as the average velocity, and the instantaneous rate of change is also known as the instantaneous velocity. So we'll be looking at those things as well. All right, so here we have the revenue in dollars from the sale of X plastic planter boxes is given by R of X equals 20X minus 0.02X 0.02x squared, and x is between 0 and 1,000. And our graph here is to the right, kind of shows what's going on. And it says, what is the change in revenue if production has changed from 600 planters to 800 planters? And then what is the average rate of change in revenue for this change in in production? So we are going from on here from 600 planters. Uh, 600 planters up to 800 planters. So that's kind of going from here, and 800 is about here probably. So looks like we're going to be going down. It's on this downward slope. So when we get done, the rate of change hopefully will be negative. So let's see what we have here. So one, let's look at what R of 600 is and then what R of 800 is. Well, R of 600 is going to be what? Well, if we plug in 600 into this, what we end up with is $4,800. And again, math is just plug that 600 here, 600 here, do your calculation, and you get that. And then if you plug in $800, what we're going to get is $3,200. So what's the change in revenue? Well, we're going from 4,800 to 3,200. So we're just going to subtract them. And when we do that, we're going to get uh, the, the second minus the first. And so we're going to get a minus $1,600. So we're going down $1,600. Now, what is the average rate of change? Well, that's again going to be our change in what's going on. And we can do this either way. Usually you're going to take the 3,200 minus the 4,800, and then 3,200 is associated with 800, and that's associated with 600. So here we're going to get what? A minus 1,600 divided by here, it looks like 200. And so, our hundreds cancel, 16 divided by that, that's going to be a negative $8 per, and we're looking at planter. So it's going down $8 per planter. Okay, and so that's going to be what our average rate of change is for this product. What about this is kind of going to the one model here with the tower. And so a small steel ball dropped from a tower will follow a distance of y feet in x seconds as given approximately by the formula y equals f of x equals 16x squared. Now the figure below shows the position of the ball in a coordinate line. Positive direction shown at the end of 0, and then 1, 2, and 3 seconds. And we're supposed to find the average velocity from x equals 1 to x equals 2 seconds. Then the average velocity in simplified form from x equals 1 to x equals 1 plus h seconds, and h cannot equal 0. And then the instantaneous velocity at x equals 1 second. All right, so let's kind of fill out what we know here. So the first thing is, one, we have we're going from 2 and 1. So we're going to basically take our second f of 2 minus f of 1 all over, and then we have 2 minus 1. Well, f of 2, that's 4 times 16, so that's going to be 64. 1 is going to be 1, so that's just going to be minus 16 over 2 minus 1 is 1. Well, that looks like it's going to be just 48 divided by 1. So the answer is going to be 48, and our velocity is going to be in feet per second. So that's what our average velocity from x equals 1 to x equals 2 seconds. Now what about 2? All right, so now we're going from 1 to 1 plus h, and so now we'll have f of 1 plus h, and then minus f of 1 over, and then we have 1 plus h minus 1. All right. Well, now we're going to have 16 times. Now we plug that in for x, so that's going to be 1 plus h, the quantity squared, minus, if we plug in 1, we just get 16. Now 1 minus 1 is 0, so on the bottom we just have h. So now we have to square this. Well, that's going to be h squared plus 2h plus 1 if we multiply it out. Then we're going to take 16 times that, so it's going to be 16h squared plus, now it's going to be 32h, and then that's going to be plus 16, and then minus 16 all over h. All right, well, 16 minus 16 is 0. Now this h can go into those, so h will go in here and cancel that one, and it'll cancel one of those. And so it looks like we're going to have 16h plus 32. And so that's going to be our average velocity in simplified form. So we've reduced it as much as possible when we go from x equals 1 second to x equals 1 plus h seconds. Okay, so that would be our answer for this one. So if we circle those or square them here. All right, so now we want the instantaneous velocity. Now the instantaneous velocity for 3, that's going to be basically, we're going to take the limit as h approaches 0 of 32 plus 16h, or 16h plus 32, however you want to look at it. And what happens is 0 goes here, so then we just end up with 32, and velocity is in feet per second. So that's just a polynomial, so we just take the limit, we just plug in the 0, and then we get that is our solution. Okay. All right, so let's stop there and we'll come back with some more definitions.